Hi everyone, welcome to the episode 3 on distributed systems. Today we are going to review time and event ordering. So distributed systems, they run on multiple nodes with the independent clocks, and without a global clock, ordering event consistently is hard but critical. First, let's take a look why even time and the event ordering matters in distributed system. First, let's take a look at the chat application. So let's say that the user A and the user B having a chat, and the user A sends a meeting at 3 p.m. User B sends two messages, one at 2:50 p.m. and another one 2:55 p.m. Let's say that the if order is incorrect, and in that case the last message is yes, let's meet, right? Then it causes the confusion. But on the other hand, for the correct order should be that the no canceled, right? So it's a clear conversation flow. Another example, let's take another example of the collaborative editing. Let's say we are using a Google Doc or similar system, and we have two users, right? User 1 and the user 2. User 1 types hello world, and user 2 inserts awesome in between. So inserts awesome like a hello awesome world. Without proper ordering, it could be hello world awesome. It makes no sense, right? It's grammatically makes no sense, but the correct ordering should be that the hello awesome world. These are very simple example, but there are number of the other cases when the improper ordering may cause an issue and even larger problems. So what are the main causes of the improper ordering? So that let's first take a look at the issues with the clock in the distributed systems. The first one is that the clock skew. In the clock skew, the difference between the node clocks, right? So let's say that we have an example and that there is a difference between the nodes. So they are very small in the 5 milliseconds or 5 seconds, but that we have that difference, right, between the two nodes. That's the first example. We have a physical difference between the nodes. And another one is that the clock drift, right? So gradually there is a divergence between the two clocks. So for example, let's say, as you can see here, so in the node A, 1 second is 1001, and in the node B, it's 1.99. So that drift, it accumulates over the time. And the last one is that the network latency. So when we are sending a messages, it takes time from one system to another, send to another system, so that the timestamp are unreliable in the ordering. So what are the solutions, right? Let's take a look at, these are the three problems that we have mentioned here, but there are more, but these three are main. But what are the solutions for this problem? The solution is to use a logical clocks, and the first one in that list is a Lamport clock. So the key insight here is that they don't use the actual time, but they count the events. So what are the rules in the Lamport clock? The first rule is that each process maintains a counter, and initially it's 0. On the local event, the counter is incremented once, and once on the send message, we are incrementing and sending the message. And on the receiving counter, what we do is we are taking the maximum of the local and the received. So let's take this very simple example. It will be more clear. So for example, let's say that on the process 1, we have a local event that goes until 3. And here, at this point, we are sending our local clock. The 3 events happened here, right? So we are sending a message to another system, to another process. And when we are sending the clock here, the Lamport clock here is 3, and then when the other system receives at 4, right, it compares that it takes the maximum of the local, which is 1 here in the process 2, and what is received is 3, so it takes the 3 plus 1. Now the time here is local time is 4. Now local event happens, and now we are incrementing that again, and we are sending that to the third process. To the third process, we again comparing local time is 1 and the receive time is 6. So we are taking maximum 6 plus 1, so which gives us 7, right? And then another local event happens, and the time here is 8. As you can see here, each process is, when we are sending a message, we are it compares that the local with the received. So we are not counting the time, we are counting the actual events. What are the advantages, right, of using the Lamport clock? The first one is that it maintains the happens before rule, which means that if the A happened before B, then the Lamport clock of A is less than the Lamport clock of B. And it's simple and it maintains the order. And what are the disadvantages? The disadvantages is that it cannot detect the concurrent events, and the two independent events may have the same ordering. Next one is a vector clock. So what we do in the vector clock? In the vector clock, it's the same as the Lamport clock, but the one difference is that instead of maintaining one counter, we are maintaining a counter for each process. So for example, in this case, we have three processes and we are maintaining three matrix with the size of 3, one for each process, right? So events known at the node, so we are maintaining the vector clock, which is that the events at the node, right? So on the local event, we are incrementing its own entry, and on the message sent, what we do is we are merging the matrix. So what is useful for vector clocks? It detects concurrent events. Unlike the Lamport clock, it can construct partial ordering, and it's used in the versioning. So for example, let's take this very simple example. Let's say we have three processes, and here what we have, right? In the step 1, we have the local time, which is 100. Then when we are incrementing and sending that to another process, to the second process, right? Here we receive the time 200, and the local time is 2, 1, and the 0, and we are merging them. We are merging, and we are taking the maximum. So here we are incrementing 2, and now the time is 220, right? Then we are sending to the third one, to the third process, and here for the local time for the third process is 001, and we are merging 2 and incrementing this one. So now we have 2 for all events, right? Now we can in case of the using matrix, we can cache the concurrency. So what are the key takeaways, right, from this episode is that the physical clocks alone are unreliable in distributed systems. Lamport clocks, they are simple, they maintain happen before order, but they cannot, in case of the concurrency, they are not working as expected. For the vector clocks, they detect concurrency and the stronger ordering info. Ordering is essential for the correctness, for example, for some crucial systems, right? Let's say that in banking, in chats, in logs, and so on. And the real world systems, DynaDB, Cassandra, and they all rely on the vector clocks.